Defining the hydraulic conductivity function and the volumetric water content function, generally the property functions, still remain somewhat of an impediment for some users for using SEEP-W. In this session, I will attempt to shed a little bit more light on the subject by illustrating cases where it is incredibly important to define the property functions very accurately, while in other times approximations are more than adequate. Hopefully this will increase your confidence a little bit in selecting proper property functions and when you should worry about defining the property functions in great detail. Once again, it depends on the fundamentals. It depends on whether we are doing a steady state analysis. Obviously, if we are going to do a steady state analysis, then all we need is the conductivity function. But as we have shown several times, in order to get a good conductivity function, we estimate it from the volumetric water content function. And if it's a transient analysis, as we have demonstrated, we must have a volumetric water content function, and then we usually estimate the conductivity function from the volumetric water content function. The functions and obviously the boundary conditions are what control the flow solution. So one of the big questions that one faces when using SEEP-W is how important are the functions? How critical is the conductivity function? Saturated flow, homogeneous saturated, unsaturated flow, layered systems, and how critical is the volumetric water content function? Let us explore these topics here with some illustrative examples. To begin with, here we have flow under a cutoff, and we know that in this particular case we have 100% unsaturated flow. So it is saturated flow. So in this particular case, the only thing we need is the Ksat, the saturated hydraulic conductivity. We do not need a function for this particular case. Now, it is important for you as the user of SEEP-W to make the decision, I do not have the possibility of any unsaturated flow, therefore all I have to do is define my conductivity with a constant, which is the saturated hydraulic conductivity. As we have pointed out earlier, in our fundamentals discussion in session number 1, we demonstrated that when we have a homogeneous case, then the pressure distribution is not a function of the property. So the pore water pressure distribution is not a function of the property. And if you want to review why this is the case, you can go back to the fundamental session at the start of session number 1. We demonstrated that for a homogeneous case, the pressure distribution is governed by the Laplacian equation, which does not include the material property. So pressure distribution is not a function of the material property, so obviously conductivity is not at all important in this particular case. However, the amount of flux is directly related to the conductivity. So if you want to define the flux accurately, then you need to define the hydraulic conductivity accurately. If the amount of flux is not all that important and all you are interested in pressure distribution, then any approximate estimate of saturated conductivity is more than adequate. So here's a case, depending on the objective of the analysis, the saturated conductivity may be important, but in some cases not important at all. To repeat, if you want to know the flux, big Q that goes through this section, then of course it is directly related to your accuracy in the definition of the saturated hydraulic conductivity. So that was an example of where we did not need the function, but now we move into a situation where we do indeed have some saturated zone and some flow in the unsaturated zone. So this is unsat. And we know, and we have seen already, that there may be some significant flow in a capillary zone. The point is, we now have flow in the unsaturated zone. And consequently, we must have a function. Now, as it turns out, I'm going to erase my highlighting here. As it turns out, in this particular case, if we have some unsaturated flow, most of the flow is through a saturated zone. And the position of the zero pressure contour is relatively insensitive to your function. And once again, the pressure distribution is quite insensitive to the function that you have defined. Now, the height of the capillary zone, as we have demonstrated here, is related to your conductivity function, and at what point does air begin to enter the soil, or the point on the function where we have the air entry value. So, since this flow system is predominantly saturated, sat is primary, the conductivity function is of secondary importance. So in a case like this, any reasonable hydraulic conductivity function representing the soils is more than adequate. Not a great deal of time needs to be spent on refining the definition of the hydraulic conductivity for a case like this. Once again, to refresh your memory, we talk about Ksat, and we talk about the air entry value, where of course the air entry value and this distance here is related to the capillary zone, or this results in tension saturated soil. As we have said, in this particular case, saturated flow dominates, and an approximate function is adequate, but it must be a function. We have a very reasonable solution here with an approximate function. Here we have no function. As a result, we get unreasonable. So we cannot do this. And the tendency is to say, I don't know anything about a function, so therefore I will simply either select a saturated constant for the conductivity, or to make the conductivity horizontal such that the K does not vary with pore water pressure. And this, of course, results in a wrong solution. And so to repeat once again, an approximate function is infinitely better than no function at all. The only time we can get away with not having a function for the conductivity if there is absolute certainty that there will be no unsaturated flow zone in the problem. Now we'll start looking at another case, and this one, the K function is of primary importance, and as happens so often nowadays, for example, in a landfill situation or a water reservoir, we often have a clay liner. And let us say that the water table is at the surface here, just for illustrative purposes, and the intent is to reduce the amount of leakage that comes through the system and goes down to the regional groundwater table. So we use something like a clay liner, and in this particular case the question is, what is the pore pressure distribution and the amount of flow, because we have two different materials here, and the flow will be 100% unsaturated or negative pore water pressures until we reach this level, after which we know it is positively hydrostatic. There are closed form solutions for this problem, and we have used SEEP-W to simulate and repeat the solution and compared it with the closed form solution, and we call this the Kish problem. And in the detailed examples that we ship with SEEP-W, this example is included together with a PDF document discussing how to set up the problem and how to analyze the problem. Notice here that we have a flux section, and we are getting 6.5 times 10 to the minus 8 cubic meters per second of flow through the system here. This is a steady state problem. So the question then becomes, how important are the conductivity functions in this case? Well, they turn out to be very important, and the positions of the conductivity functions for the fine soil and the coarse soil and the relative positions of these functions is what controls the flow through the system. So to highlight the results, here are some of the key points. And number one is that the pore pressure everywhere is negative. So this is flow in the unsaturated soil. Now we may have some tension saturated zone here, which is the capillary zone. However, for most of the section, the flow is unsaturated. Now where we get this vertical zone here, where the hydraulic gradient is 1, depends on the hydraulic conductivity functions. And you will notice here that where we have a negative pressure of around 5 point something kPa is where the hydraulic gradient is 1.0. If we follow this exact same pressure onto our function, we notice that at about 2, 3, 4, 5 point something, that if we go up to our function, we land up on the function where we have a flow of 6.5 times 10 to the minus 8 per area. The area is not exactly 1. If we normalize it to an area of 1, we get a conductivity of 1.37 times 10 to the minus 7 cubic meters per second of flow, or meters per second of conductivity. So this value plots right here on our function. So now you can see that the relative positions and the shapes of the conductivity functions govern the behavior. In other words, for a situation like this where we have 100% of flow where the pore pressure is negative, the relative positions of two functions for different materials become extremely important. Here is a real field case. This is a open pit mining operation, and here is a waste dump, and at this mine site, though they had a large slope failure in the waste dump, and the slope failure produced this headscarp which exposed the dumping of the waste rock. And clearly you can see the stratification in the dumping of the waste rock. And the flow is rather complex in this particular situation. And so if you look at it carefully on the stratification, it appeared that the coarse material was rather dry, but next to the coarse material in the fines, there was oxidation, and it would appear, looking at this cross-section of the waste rock pile, that the flow was taking place in the fine soils and not in the coarse soils. The unsaturated soils group at the University of Saskatchewan became interested in this site and were invited to view the site, and the question became, can this observation be modeled, and can it be explained based on unsaturated soils theory? And so one of the graduate students, Lori Newman, did her master's thesis on this project, and she built an apparatus where the apparatus is approximately 1.4 meters high. And the idea was to have two different materials, one a fine material, one a coarse material, and then to drip water on the surface and try and see if it could be demonstrated as to where would the flow go. And so there was a collection system at the bottom here which measured the amount of water that would come through the column. And indeed, here are the conductivity functions, and various flux rates were applied to the column. We will highlight here only two flux rates. One flux rate was less than Ksat for the fine sand, and another flux rate was higher than Ksat for the fine sand. So two different flux rates, and the question is, where would the flow follow within this column? And here are the experimental results and a highlight of the results. And when we had a low flux, a small infiltration, so to speak, a low flux, 100% of the flow went through the fine material. Hardly any flow, and according to the lab measurements, there was no flow that went through the coarse material. Any water that was dripped onto the coarse material went sideways and into the fine sand and dripped out of the fine sand. Now, if there was a high flux, then the situation was somewhat different. More than half of the flow went through the coarse, and almost half of it went through the fine material. So where the flow goes in a layered system like this depends on the rate of infiltration, and it depends on the relative position of the hydraulic conductivities next to each other. The question was, can we simulate this effect with SEEP-W? And indeed you can. Once again, there is a detailed example that we ship with the software, giving the details of the numerical analysis here. The detailed example is called preferential flow in vertical layers. And when we have a low rainfall rate or a low infiltration rate, we see indeed that most of the flow goes in the fine sand. About 93% is in the fine, only about 7% is in the coarse sand. So it's very, very close to what was observed in the laboratory test. If we increase the infiltration rate or have high rainfall, then of course once again a significant amount of the water flows in the coarse material and a smaller amount flows in the fine material, consistent again with the laboratory observations. Now let us look at this behavior in the context of a soil cover system. Assume that there is some material that here needs to be protected, either some rock waste or some landfill, and the idea is to prevent the infiltration from migrating down into this material down here, and the idea is to try and take the the precipitation and carry it away to some collection system. And the question becomes, should the fine material be over the coarse material, or should the coarse material lie over the fine material? And intuitively we want to say the coarse material is more open, therefore obviously we should have the coarse material on top of the fine, and that way the coarse material could carry away any infiltrated precipitation. However, the situation is not quite that simple. To a large degree, it depends on the rate of infiltration. And when we have low to modest rainfall rates, then this is the design that we should adopt. The flow comes into the fine sand and then is drawn away into some collection system over here. Now it is true that if there should be a cloudburst and there is some very intense rainfall for a short period of time, that the precipitation would indeed drop down into the coarse material, and it is possible that some of it might drip down into this zone here. But in an arid area, a region of the world where rainfall rates are quite small, then we should select a design with the fine material over the coarse material, because that would be the most effective for most of the time to carry away any precipitation that infiltrates the layered system. Here is an interpretation of the process. A very simple illustration, and that these are our conductivity versus negative pore water pressure, and this is the fine material. And we demonstrated a few slides ago that when we have vertical infiltration and the hydraulic gradient is 1, then the infiltration rate is related to the conductivity. So we can think about low conductivity at a gradient of 1 would give us a particular pressure distribution, but it relates the two conductivities, and so this would be a modest, low to modest rainfall rate, and in this particular case here, the conductivity of the fine sand, of course, is much higher than that of the coarse material, and therefore the flow goes where the least of energy is required. In this case, it goes through the fine material because it has the capacity to carry water with less energy than does the coarse material. Now, if the rainfall rate should be intense, which is the green line here, now of course the conductivity in the coarse material is higher than in the fine material, and consequently the flow once again seeks the path of least resistance, and therefore the flow now is in the coarse material. So to repeat, the key issue is that the flow process is governed by the relative positions and shapes of the two hydraulic conductivity functions for the contrasting materials in the layered system. As we have already mentioned, in many cases we have facilities where we have a clay liner at the bottom of a reservoir or the bottom of a landfill facility or something. The whole idea is to mitigate and reduce the amount of leakage into the underlying groundwater at depth. And so often we make use of a clay liner. Regulatory agencies then make it mandatory to monitor the performance of the clay liner and to report how successful is the clay liner and how it is performing, and part of the conditions of proceeding with the project. And so often it is necessary to build a collection system, and a collection system like this is called a lysimeter. And the tendency is to make a very large pan here. And the hope is that any water droplets that come along will collect in the pan and will eventually be taken to some collection system. And the collection system will be such that we can monitor the amount of flow that is coming through the clay layer. Unfortunately, this type of a measuring system has to be designed very carefully. Once again, it is purely unsaturated flow, and so if we are not careful, then the flow will not collect in the pan. Here is a flow line from a SEEP-W analysis, and notice how the flow bypasses the collection system. And this is related to the pressure contrast in the pan and the pressure contrast here at the bottom of the pan. And so we see here that in all likelihood the pore pressure right at the base of the pan is near zero, and here the pore pressure is highly negative, and so there is a gradient for the flow to do this. And this has been modeled as part of a study, and here is a reference at the end of this session, and in the proceedings is a list of references. If you have more interest in this type of a situation, I would refer you to this reference, which is listed in the SEEP proceedings. Very briefly, the objective to solve this situation is that it is necessary to ensure that the pore pressure on the outside of the lysimeter is the same as the inside of the lysimeter, and when this is done, then the collection system in fact does work. I won't go into any more detail here except to note that here we once again have 100% unsaturated flow, and to model this accurately and realistically, it is mandatory to have some highly realistic conductivity functions for the two contrasting materials. In other words, the hydraulic conductivities for a case like this are incredibly important to the analysis and to the understanding. To summarize then in this PowerPoint slide, 100% unsaturated flow, the property functions are critical. The function must be realistic and defined with great care. The key issue is the position and shape, as I've said several times, of the property functions relative to each other. It's not the absolute position so much as the relative position to each other. And the response is dependent on the infiltration rate. As we have seen several cases, when the infiltration rate is low, we get one response. When the infiltration rate is high, we get another response. Returning then to the question, the importance of the conductivity function. Completely saturated, the function is not important at all, and the property functions are not relative. Saturated flow, where saturated flow dominates, mainly lateral flow like through a dam, we need a function but an approximation of the function is more than adequate. When we have purely unsaturated flow and unsaturated flow dominates, then the conductivity function is very important. The next question, what is the importance of the volumetric water content function? Any transient process is sensitive to the volumetric water content function. In other words, the volumetric water content function is extremely important to any transient process. Recall from our earlier discussions, it is the volumetric water content function that describes the soil's ability to store and release water, and it's the slope of the curve that's directly related to the rate of change of the water content, which is related to real time. Related factors, of course, it depends on the initial conditions. If you have a very dry starting condition, then it affects the time to reach a saturated condition. Or vice versa, if it's very wet and we want to drain the soil, it is a different time. So the time is affected by the initial conditions. And as we know that the conductivity is related to water content changes, and as a result, the process of wetting up a soil is a much different time than the process of drying out the soil. Wetting up a soil, we know that the conductivity increases as the pore pressures decrease and we reach saturation. As a result, infiltration doesn't take as long as, for example, drying out a soil. Drying out a soil, the conductivity decreases continually, and as a result, it's more and more difficult to remove water from the sample under drying conditions. So it depends on the direction of wetting or drying. And of course the boundary condition that depends on the rate of infiltration for the examples, for example, as we have seen. The important thing to remember is that the water content function is very important in any analysis that involves real time. If we want to talk about days or years or months, and we want to predict time with any reliability, then the water content function is extremely important. Even in consolidation, we need to define the volumetric water content function, or the slope of the function where the pore water is positive, which is related to m sub v, is directly related to the real time it will take, for example, to dissipate excess pore pressure due to external loading. So this brings us to the end of our discussion on how important is the function, how important is the conductivity function, and how important is the volumetric water content function. And the short answer, it depends on the conditions that you are trying to analyze and the type of process that you're trying to analyze in the field. We have seen that in some cases the functions are not important at all, while in purely unsaturated flow the functions are extremely important. So here is a brief summary of the importance of these functions, and hopefully it will give you a better comfort level on using these functions in SEEP-W.